Okay. Okay, yes. Take care, Sadie. All right, now, what I want to do is I want to talk about phase change. The material we're going to use is called water, H2O. It's a substance. There are two types of substances. There's a compound, which is made of two or more elements. There's an element, which is just made of one element. Clear? This is made of hydrogen and oxygen. It's covalently bound, and it's a molecule. And it has specific, unique, characteristic properties. And some of those, take care, Bree. Sorry we didn't do more, but that's okay. Again, we'll have another time too.
All right.
Okay, now, the process in which the phase change happens is the same for all phase changes. There are variations in each phase change depending upon the compound or element involved, melting, solid, liquid, gas, freezing, boiling, etc. But it's basically the same idea. We're going to take water from negative 20 degrees Celsius, solid ice, to steam. Steam is a colloquial way of saying gaseous water at 120 degrees Celsius, okay? Let's just look at it briefly and see if the chart makes sense from your experience in life, your common experience, and chemistry, okay? Here I have a graph. Degrees Celsius versus time. I have ice. It's starting 0 time. It's at negative 20 degrees Celsius. Do you understand that that's ice? Negative 20 degrees Celsius. Do you understand that? It's ice. Okay. I warm the ice. The ice is going to increase in temperature in a linear fashion until it reaches 0 degrees. Then it goes through a phase change. It turns from a solid water at 0 degrees Celsius to a liquid water at 0 degrees Celsius. Now, then, it changes from liquid water at 0 degrees Celsius to liquid water at 100 degrees Celsius. Clear? Then it turns from liquid water at 100 degrees Celsius to gaseous water at 100 degrees Celsius. Then it turns to steam. So there are actually 5 sections to this graph. There are solid on that side, solid liquid on this side, liquid on that side, liquid gas on that side, and gas on that side. You see there's 5 sections? You see that? Okay. There will be 5 separate calculations. There will be 5 heats. There will be Q1. There will be Q3.
Mr. Marticelli, Mr.
Correct.
Marticelli, could you
There will
contact
be
me
Q5.
Mr. Marticelli, please contact me. Thank you.
What happened to 2 and 4? Well, this is actually a heat, and that's going to be number 2. This will be number 4.
No, get up.
Okay? You can open the door, that's fine. Just do it quickly.
Door's open.
Okay? All right, now. Everything all right? They wouldn't give it to you?
You have to get it from the person.
Okay, that's fine. That's not a problem. We can talk about it later.
Okay.
Okay, now. So solid, liquid, liquid gas,
Manny Brown.
Gas.
Manny Brown, come to the
Understood?
main office as soon as possible.
You kind of feel like you're working at Sears department store. If that thing goes off one more time,
You're going to do what?
I'm going to
Tell me.
be annoyed, okay? All right. So, yeah, so far so good? So far so good? Okay, now. There are, again, 5 separate heats. There are 5 separate heats. The first heat is going to be the product, mass times the change in temperature times the specific heat capacity of ice. The specific heat capacity of ice is 2,020 joules per kilogram Kelvin. What's the difference between joules kilogram Kelvin and joules kilogram degree Celsius? Is it the same thing? It's absolutely the same thing. 1 degree, because 1 degree Kelvin is the same as 1 degree Celsius, the same gradation. There are 100 Kelvin between melting and freezing. There's 100. There are. There are 100 degrees Celsius between freezing and boiling. Do you get it? There's 100 Kelvin, 100 Celsius. So per Kelvin, per degree Celsius, same thing. Okay? Now, I'm going to erase the graph in a minute and do part 2, and we'll actually do the calculations by remembering what the graph was. So let me just quickly get through this, and then I'm going to do the next lesson. This will kind of be in 2 parts. Okay? So, M delta T, specific heat capacity of a solid. This one is going to be the heat of fusion. We're going to put that in. We're going to put M delta T, the specific heat capacity of a liquid. That's that.
Okay.
We're going to put the heat of vaporization in. And we're going to put in heat 5 will be mass delta T, specific heat capacity of a gas. Clear? Right? Now, just a side note by looking at the graph. Why is a steam burn much worse than a boiling water burn?
Steam's hotter.
Steam is hotter. Steam has more heat. Look at this. This is water at 100 degrees. This is steam at 100 degrees. Look how much heat goes in there. You see that? Yes? You see that?
Yes.
So look at the heat of vaporization of water. 2,260,000 joules per kilogram. That's a lot of heat. So this water has 2,260,000 less joules per kilogram than steam does. Got it? Yes? Okay, remember, this is all steam, this is all liquid water. All liquid water, all gaseous water. Are you with me?
Yes.
Yes? Okay, I'm going to stop, I'm going to come back, I'm going to do the calculation, and we're done. Clear?